Let's talk about an integration technique that not many calculus students get to see. In calculus 1, 2, or 3, we're always working around the x and y plane. But what happens when you're given specific functions that are going to require us to now start thinking about the complex plane? And in the complex plane, we do something called contour integration, where instead of integrating from one x value to another, we're now integrating about a contour. Now, this might seem a little complicated, but let me go ahead and give you an example that might motivate you to study contour integration. So here we have this integral from negative infinity to infinity that's a little difficult to solve. In the real world, we're always integrating from negative infinity to infinity, but in the complex world, we have the real and the imaginary axis, and we can go ahead and complete this closed contour by going from negative infinity to infinity and then creating a half circle where the radius is extending onto infinity. Now, this function is really nice because there's no discontinuities whatsoever on the real axis. And whenever that happens, we can go ahead and draw a contour like this. So now we're going to rewrite the integral so we know that we're integrating around the contour and we're changing our variable into z's because we're working with complex numbers. Now, one thing we're going to do is work with the Euler formula that tells us that the real part of that is only the cosine. So then now we can rewrite our integral into something that looks like this, where we're simply just calling for the real part of e to the iz. And in this particular case, we're really just trying to find when the bottom is equal to 0. And in the world of context integration, you need to look for something called singularities. You do some basic math and you're going to see that we find two complex numbers. We have a positive and a negative, and the only one that exists within the contour is going to be the positive I over 2. And this is what we're going to be working with. We're going to use Cauchy's residue theorem. And in this case, because we only have one singularity, this tells us that the contour is equal to 2 pi I times this limit right here, where zi is your singularity. Using the singularity that we found, which was I over 2, we go ahead and plug this in to the limit. Now, I highly encourage you to solve this on your own, but you're going to see that on the top, we're going to be left with e to the negative 1 over 2. The z minus I over 2 cancels out so that we have a 4i on the bottom. And in this case, the I on the top and bottom cancel out. The 2/4 can turn into a 1/2. And there's nothing but real parts in this particular answer, so I can get rid of the real part here, which is going to give me this nice solution of pi over 2 root e. As I mentioned, I did this to motivate you for contour integration. I left out some things like Jordan's lemma, which helps us solve this integral, but at the end, this is the idea of Cauchy's residue theorem and how to use contour integration.